If the distribution is look like bell shape, then empirical rule says that 68.27% of population data fall between one standard deviation away from the mean, and 95.45% of population data fall between two standard deviation away from the mean, and 99.73% of data falls between three standard deviation away from the mean. Here is the empirical rule. Now, if you look at the second line, this means about 95.45% of population data is in between mu minus 2 sigma and mu plus 2 sigma. Using this, we can conclude that for a sample, it is more likely that its minimum and maximum values in between x bar minus 2s and x bar plus 2s. This means we can get crude approximation to sample standard deviation as below. Standard deviation is close to the range divided by 4 if the distribution is bell-shaped. The coefficient of variation measures the variability of population relative to the magnitude of the population mean. For example, let's say you have two datasets about grades of history exam and grades of math exam. Here is the dataset. Now, which dataset has more variability? It is hard to say because there are two types of exams. You cannot compare apple and oranges. You cannot just use standard deviation. You have to think about the mean too. So what can we do? We can calculate coefficient of variation. This will give us rough idea about which grade has more variation compared to other. One thing you should really notice about coefficient of variation is its unitless measure. So for history, our coefficient of variation is 0.333. For math, it's 0.375. You can express this as percentage too. Now look at the data. In history, the standard deviation is 20, but coefficient of variation is less than the coefficient of variation for math. So compare their respective mean. History has less variation compared to math. Math has more variation respect to its mean. So because of the unitless property of coefficient of variation, you can compare two data sets like weight, which use kilogram, and height, which use meters as measurement units. Now coefficient of variation use only for ratio data. That means data type with natural 0 point. You should Google and find more detail about nominal, ordinal, interval, and ratio data type. 5-number summary consists of following numerical summaries: minimum, first quartile, second quartile, third quartile, and maximum. Let's calculate 5-number summary for this dataset. We are going to use R to calculate 5-number summaries. So here is the dataset: 22, 115, 185, 189, 221, 230, 233, 237, 258. And when I run this summary function, I get the 5-number summary. So minimum, first quartile, median, mean, third quartile, max. Mean is not part of 5-number summary, but the function give that one too. Okay. Now the box plot is created using 5-number summary. We can use it to look at the symmetry of the distribution, and it's also incorporate numerical measures of central tendency and location to study the variability of the data set and how the data are concentrated. So all of these things we can look from the box plot. Now how do you construct box plot? First you draw a box around first quartile and third quartile. Then you draw a line inside the box at the median. Now what you do, you calculate 1.5 times IQR. IQR means interquartile range. And then what you do, you draw a line goes from the lower end of box. That means from Q1 to the smallest observation that is not potential outlier. And you do the same for the for the upper end of the box. You draw a line from Q3 to the largest observation, which is not a potential outlier. And any outliers, that means any observation outside of this 1.5 term IQR, are shown separately using either stars or circles. Now the center of the distribution of data is indicated by the middle line in the box plot. And we can see the measure of variability using the interquartile range. That means the length of the box. And additional information like skewness can be obtained from the length of whiskers. The longer one whisker relative to other one, and the more skewness is in that tail. It's skewed to that side. And we can also make an assessment about the outliers. So here is a data set. 22, 115, 185, 189, 221, 230, 233, 237, 258. This is the same data set we used previously in our output. So we calculate the minimum. Here is the minimum. Here is the Q first quartile, second quartile or median, third quartile, and the maximum. Now we can calculate interquartile range. That means Q3 minus Q1. Let's give you 48. Let's calculate 1.5 term IQR. That means 1.5 term 48, which gives you 72. Now remember, the whiskers extend from first quartile to the smallest observation, which is in between Q1 and Q1 minus 1.5 term IQR. So if you subtract 1.5 term IQR from Q1, you get 113. So this means first 22 is potential outlier because it's outside. And the smallest observation before 113 is 115. So the whiskers extend to 115. Now if you go to the upper end, Q3 plus 1.5 term IQR gives you 305. So whiskers can go until 305. But the maximum observation we have is 258. So whiskers extend until 258 and that's end at that point. So let's draw the box plot. So first we draw the box around Q1 and Q2. So let's say this is my scale. So here I have, this is not a nice scale, but let's just pretend it's in a scale. 233. So I draw a box around this between first quartile and third quartile. Then I draw a middle line. This is median. This is median. Then now I extend the low end of whiskers to 115. So let's say this is 115. And the upper end to 258. So let's say this here is we have 258. Now 22 is potential outlier. So 22 is somewhere here. And I have to use a star to denote that. So this is the box plot for that data set.